Building a modern commercial airliner is an incredibly complex puzzle, and for decades, there has been one absolute rule: nobody solves it alone. Look at this supply chain map for a standard jet. Whether it rolls out of a Boeing factory or an Airbus hangar, you're looking at tens of thousands of parts, from raw titanium to flight control computers, sourced from dozens of different countries. This is the Sukhoi Superjet 100. It was designed to capture the regional travel market, and originally, Russia built it by playing exactly by these globalized rules. The math is simple. Keeping a commercial jet program alive requires a constant, uninterrupted flow of international cooperation. But recently, an encompassing wave of global sanctions hit the Russian economy with a speed and scale that caught the entire sector off guard. For the Superjet program, the impact was immediate. Look at the supply map now. The crucial imports it relied on, the flight computers, the landing gear, and the European-built engines, vanished overnight. Russia spans 11 time zones. Without a reliable domestic fleet, the basic connectivity of the country's remote regions effectively dissolves. Yet their flagship regional jet was suddenly paralyzed right on the assembly line. So how exactly does a nation keep its citizens moving when it has been completely locked out of the global aerospace ecosystem? The Russian aviation sector didn't scrap the grounded Superjet program. Instead, they doubled down, pivoting to a total engineering overhaul they call the SJ-100. Here you see the physical reality: airframes stripped down to the metal. The goal is replacing almost every internal system, manufacturing 97% of parts domestically. Engineers are tasked with reverse engineering highly complex flight avionics from scratch, entirely without access to Western blueprints. This strategy is called autarky, creating a completely closed-loop, self-sufficient manufacturing economy. It goes against everything the commercial aerospace industry has practiced for the last 40 years. Stamping out individual parts in isolation is one thing. The real test is taking thousands of brand-new, completely unproven domestic components and getting them to communicate flawlessly inside a commercial airliner. All of those new components, however, pale in comparison to the single hardest problem on the aircraft: replacing the imported European engines with a homegrown turbofan called the PD-8. Check out this cross-section of a modern turbine spinning rapidly inside a commercial jet engine. Building something like this from the ground up is widely considered one of the most difficult engineering feats on the planet. The internal environment is incredibly violent. The operating temperatures inside the combustion chamber routinely exceed the melting point of standard industrial metals. To survive that heat and kinetic stress, the turbine blades must be cast with microscopic, millimeter-perfect tolerances. Even a tiny flaw can cause the metal to shatter at high speeds. Normally, developing and testing an engine of this caliber takes a full decade. Trying to fast-track that process to bypass sanctions carries high inherent risks to long-term safety and reliability. If the PD-8 engine cannot perform safely day after day, the rest of the aircraft doesn't matter. Without it, the SJ-100 is just a multi-billion-dollar paperweight. The engineers are rapidly approaching their deadline. The SJ-100 is nearing the end of its development cycle, with initial deliveries slated to begin soon. Once it rolls out of the factory, it is expected to become the sole heavy-duty workhorse keeping Russia's internal regional travel network alive. But creating a successful prototype is only half the battle. Now, Russian factories must scale up production of these highly specialized parts, doing so without access to imported Western machine tooling. A perfectly engineered prototype will pass a certification test, but the production models rolling off the line have to endure the repetitive, grueling strain of multiple commercial flights every single day. This entire project is functioning as a live experiment with long-term consequences for how international industrial policy is shaped. If the SJ-100 flies reliably and scales effectively, it proves that a sanctioned nation can successfully sever its ties and bypass established global aerospace monopolies. But if the supply chains crack or the engines fail to hold up to commercial wear and tear, it proves something else entirely. It cements the fact that 21st century aerospace engineering requires a global network to survive. That is exactly why the rest of the aviation world is tracking this program so closely. The ultimate fate of the SJ-100 will serve as the definitive stress test for industrial self-reliance.